a function which graph is non-vertical, which the graph is in a non-vertical line.
In a non-vertical line. Tell me what a non-linear function.
A non-linear function doesn't have a constant rate of change and isn't a line.
Right. It could go up and plateau and go up again and plateau again and those kinds of things. So that would be your non-linear function. What is a discrete domain? Go ahead, Chloe.
A discrete domain is a set of input values that consist of only certain numbers in an
Interval, blah, blah, blah. In an interval. So it's going to be specific numbers that can't be broken into parts. So it's like saying at a specific rate. Interval would be like 1, 2, 3, 4, 5, not 1/6, 1/8, 1.5, those kind of. So when you hear the word discrete, think whole numbers. So when we're doing word problems, if I talk about inputting a group of 10 students, can I have a half a student in a problem like that? No. So that's automatically you can't have a portion of the whatever the input value is. That's a discrete domain. A continuous domain can be broken up along the line. So think like granola bars. Can I eat a half a granola bar?
Yeah.
Sure. So that would be a continuous input value. That's the easiest way I've found to remember the differences. Discrete has to be consistent, same whole numbers. Continuous can be anything along that line. Okay? All right. So a linear equation in two variables. What are our two variables? X and Y. Is an equation that can be written in any form, into the slope-intercept form, which is, we did it all week. Yep, say that louder.
Y equals mx plus.
No, girls, you want to join in? All right, just making sure you all know. What does M stand for? What is M in this equation?
The
slope. Come on, you gotta remember. Slope. What is the B?
The B is where the where it started.
Which is called the
y-intercept.
So the B is the Y. Okay, this is something you've got to know, or I'm gonna drop you back down to the other class and make sure we're doing the same thing. You got to remember this. M is your slope. B is your y-intercept. You have to know this. So the graph of a linear equation, whenever you hear that word linear equation, you know the graph's going to be a line. So we're fixing to do this example, but it'll show you. A linear function is also going to be a graph that is a non-vertical line. We already talked about that. And then a non-linear function does not have a constant rate of change because it's going to dip, plateau, curve, all those things. So for your first example, and in your journals, just do a quick sketch of these. It doesn't have to be like written out perfectly. Just like draw the little coordinate and then draw the blue line and call it a day. So we're going to decide whether the graph is a linear graph or not, a linear function or a non-linear function. So looking at A, would you call that a linear function? No, why not?
Because it goes it's not a straight line.
It's not a straight line. Simplest way to explain it. It is not a straight line. All right, what about B?
Yeah.
Would that be a linear function?
Yeah. It's a straight line.
Correct, because it is a line. Super hard. I know y'all can handle this one. Questions? No questions? All right, good. So let's look at example 2. So you can write this one in your journal. Does the table represent a linear or non-linear function? You do need to write this down. Okay, we did this in the first lesson, but I know it's been a big minute since we had our first lesson. So let's look at the input versus the output. We have 3,36 is one of our points. 630, 924, and 1218. Would you consider that a Well, first of all, let's look at the pattern. Is x going up at an equal interval?
Yes.
Yeah, 3, 6, 9, 12. It's going up by what?
Threes.
3s. What about our y?
Decreasing by 6.
Decreasing by 6. So is that a constant rate of change?
Yes.
It is. So this would be a linear function. Linear function. I keep wanting to say equation. Sorry. Linear function. So now let's look at B. The x values go up by what?
By 2.
By 2. 1 to 3, 3 to 5, 5 to 7 is up by 2. However, what do our y values go up?
By 7,
11,
11.
15.
7, 11, 15. So is this a constant rate of change?
No.
No, everything differs. So it's going to do weird things as you graph that. So this is not constant. So is this function linear?
No.
No. So this is a non-linear function. It just means it's going to have weird plateaus and curves and things. All right, any questions on how to solve for linear versus non-linear?
That's a good question.
Yeah.
So for one, please write it down on paper like that.
No, I just wanted it in your journal.
Okay.
Good question. It's just in your journal to help you. All right, so let's do monitoring progress 1 through 4. Bless you, by the way. Okay, so let's look at example 3. Which of the following equations represents a linear function? And then tell me why. So we got a lot of funky ones happening here, right? Okay, let's look at the first one. Y equals 3.8. Would that be a linear function?
No. Yes.
Yes, because
Does it have a slope?
Yeah.
What's the slope?
3.8.
No. Slope is m, which would be in front of an x value. Is there an m and an x value? There isn't. But if there isn't, what is the slope? 0. So the slope is 0. So could I write this as y equals 0x plus 3.8? Yes. So then it would be a linear function. This is a horizontal line. Right?
Yeah.
So if I were to graph that, if I were to graph this one, I would go y to 3.8, which would be right here, and it would just be a horizontal line. So that one would be a linear function, because that's a line. Okay? The next one, y equals the square root of x. Is that a linear function? No, the square root of x is going to give you some really funky number. So it's actually going to be a curved line.
Square root of x. What would x be?
Whatever x is.
Well, it's whatever x point is. Okay, what about, we're just trying to, remember all of these, you're trying to see if you can write them in what form?
Y equals mx plus b.
There it is. Okay?
Yep.
So we're just trying to see if we can write that. So the second one, no. The third one, y equals 3x. 3 to the power of x, excuse me. Can I rewrite that into y equals mx plus b?
No.
Question mark? There's not a simple way to rewrite that into y equals mx plus b. So that one also would not be a linear function. All right, let's look at y equals 2 over x. Can I rewrite that one into slope-intercept form?
Yes.
Maybe. Let's test it and see.
And then 2 over x.
So how would I move the x?
Move it over.
Right? So then I have xy equals 2, but I need to get y by itself. So it keeps turning around to where x is on the bottom, no matter what we do. So the answer would be
No.
no. So you cannot write that as a linear function. Okay? All right, now we have y equals 6, open parentheses, x minus 1. Can I rewrite this one into our linear equation?
Yes.
Yeah, we just distribute, right?
So it's x.
So now it's in slope-intercept form. So that one is a linear function. Okay, what about our last one?
X to the power of 2 minus y equals
The
0.
power of 2 is 2, like, quite simplified.
When you see anything to the power of 2 that is not going to be a linear function, you're going to have some kind of squiggle in your line. So it does. I mean, you could rearrange it, but it's not going to do you any good. Okay, here's some examples of the rewriting. We did those.
Yes, ma'am.
All right, any questions on those?
No.
Okay, so if you see an exponent, not a linear equation. That's an easy, quick one, right?
Yes.
If the x is underneath a number, not a linear equation because you can't rewrite that one. All right, so do monitoring progress 5 through 7, and then we'll do the next part. All right, so just real quick on your concept summary. If you feel a little shaky with everything we've gone over in this lesson, I would write this in your journal. So these are the 3 different ways to talk about functions and to figure out whether they are a function or they're not a function. Well, technically there's 4 here because we also have the equation. Is this written in slope-intercept form?
Yeah.
Y equals x plus 3?
Yes.
Yes, it is. Then they created an input-output table. Do we have a individual output for every input? Yes. So now we also know it's a function. That was from lesson 3.1, 4.1, 3.1. This is a mapping diagram. It's just a fancier version of a table. They look identical. Is there one output for one input?
Yes.
Yep. And our last way to test is does it create a straight line? So these are all ways to test whether you are looking at a linear function. All right? Excellent. So a solution of a linear equation in 2 variables. So you're going to look for a solution that is an ordered pair. So you're going to always look to tell me an answer that has an x comma y. You must write it like this or you will lose points. So parenthesis x comma y parenthesis. Okay? That solution makes the equation, the y equals mx plus b, true. So sometimes you're going to graph it. Sometimes it'll be, you could graph it on a number line. Sometimes you could graph it on, you're most of the time going to graph it in a coordinate plane. So here's our discrete and continuous domain that I kind of talked to you about at the beginning. Notice the discrete is a set of input values that are solid whole numbers. So that's the input values for this particular equation. A continuous domain is everything in between, including the little half or 1/8 or 1/6 or whatever. So again, think about when you're discrete, can't break it into parts. Continuous, you can break it into parts. That's the best way to think about it when you're doing word problems. Or when you're looking at a set of numbers. If you see 2.6 and 3 and 6.7, that's going to be which one?
Continuous.
Continuous. If I see 10, 20, 30, 40, 50, it's going to be discrete. All right, so let's look at example.
Example,
Is this 4, question mark? Example 4? Excellent. So first of all, the linear function y equals 15.95x. Is that a linear equation?
Yes.
Yes. It just doesn't have a plus b. That's fine.
Okay.
Plus 0 is correct. Represents the cost where y represents dollars, x represents the number of tickets for a museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Is the domain discrete or continuous? And tell me why. And then graph it using its domain. So first of all, what are we inputting? What's our input item here? I don't want a number. What is the object? That is the input item. So what? First of all, is y input or x input? X is our input. So what is x representing? Tickets. So can I have a half a ticket to get into a museum? No. So what kind of domain?
It's a discrete.
Discrete, because you can't have a half a ticket. So you already know that for A. And then we need to find the domain, which is all of the input values. Correct? Domain is input. All of the potential input values for this equation. All right, so there you cannot buy part of a ticket. Because X represents the number of tickets, it must be a whole number. What is the maximum number of tickets that you can buy?
4.
4.
So you go to 4.
So then the domain would be
Up to 4.
the whole numbers up to 4. Could I buy 0 tickets? Sure. You can choose not to purchase anything. So that would count as part of your domain. And then I can buy 1 ticket, 2 tickets, 3 tickets, or 4 tickets. I could say I'm not going. So I didn't push a button. So understand what the domain is?
Yes, ma'am.
And we understand why it's discrete.
Yes, ma'am.
Excellent. So now we're going to graph it. Wrong button. Okay, they made their input-output table. Do I care if you have an input-output table? Please say no, because gross.
No.
I want you to graph it. Okay? So you can take all of the points that we had, the input values 0, 1, 2, 3, 4, plug them into your equation, find the y value, and graph all these points if you would so choose. Or we can take our equation. What was our original equation?
Y equals 15.95x.
Y equals 15.95x. Can I graph that?
Yeah.
What's my b?
Your b would be 0.
So this is a real life word problem, isn't it?
Mm-hmm.
So not likely to need the whole coordinate plane. So my x value is 15.95, so I'm going to say 5, 10, 15, 20. Well, this is 1, 2, 3, 4, sorry. 1, 2, 3, because that's how many tickets you can buy.
And then the top
This would be 5, 10,
15, 20.
15, 20. So 1 ticket cost me how much?
15.95.
Yeah, I probably should have made that bigger, huh? So let's go 15, 30, 45, 60, 75. That makes more sense, right? Because each ticket is at about $15. So I'll go up by $15 each time. So my first ticket is just a little over $15. My if I bought 2 tickets, it'd be a little over $30.
$30.
So on and so forth.
So on and so forth.
Can you do the numbers with like the input next to the first dot 0, comma 15.95?
It'd be 1, comma 15.95.
Oh, okay.
Because you bought 1 ticket for $15.95. 2 tickets would cost you
However much that is.
however much that is.
And then 0. 0.
31.9. Okay. I don't need you to label it. I want to see your graph.
Oh, you didn't do that?
Yeah, it told you to graph it. I just need you to graph it.
The 0 would just be 0, 0.
Yep. Because I didn't buy any tickets, so I didn't spend any money.
Okay, I like that.
You really only need to label 2 points on the line. So
2?
yeah, so I labeled this one and this one.
Yeah, I like it.
If you want to label them all, go for it. All right, any questions on how we did that? Not too terrible. All right, so you're going to do monitoring progress 8, and then we'll do example 5. All right, so example 5.
ABC.
Example 5, a cereal bar contains 130 calories. The number C of calories consumed is a function of number B of bars eaten. Does this situation represent a linear function? So first of all, can I write this as a linear function? So C would be our Y and B would be our X, because B is representing the granola bars that we're eating, or cereal bars that we're eating. So that's the input value, correct? So that's how I know the number of calories eaten is dependent upon the number of cereal bars we eat. So that's why I know I can write C equals, how many calories is a bar?
130. 130 B
130 per bar.
plus 0.
Yeah, you could say plus 0 because we haven't eaten any cereal bars. Is that a linear function?
Yes.
Yes.
Yes. So A would be yes. because as it increases by 1 bar, it also increases by 130 calories. All you need to be able to tell me is it's a constant rate of change, or you could say I can write it as a linear function. All right, B. First of all, is the domain discrete or continuous?
Continuous, because you can eat like half of a bar.
Correct. Continuous. I could take 1 bite of a granola bar or cereal bar, and it would count. I'd have to count however many calories out of that bite. So this would be a continuous. The domain would be, you're going to have a range of any value greater than or equal to 0, because I could choose not to eat any cereal bars and not eat any calories. Otherwise, it's everything higher than 0. So what's a way you could write that? You're on the right track. All you would say is D is greater than or equal to 0. Or B, sorry, not D.
Yeah.
The domain is B has to be greater than or equal to 0. Okay. Then the last one is graph it using its domain. Bless you. All right, so again, they made an input-output table, but you can just choose to graph it. So am I going to have any negative values here? No, because I can't negatively eat. I mean, I guess you could throw up, but that doesn't count. All right, bars are going to be, 1 bar, 2 bar, 3 bar, 4. Ooh, that's a weird. Okay, and then we're going up by how many calories per bar?
130.
130.
130.
So I'm going to say 130 here.
390.
390.
430.
430, sure, we'll go with that. All right, so what does 1 bar cost me? Well, what does no bars cost me?
0.
0 calories. What does 1 bar cost me?
130.
130. 2 bars.
260.
So why did we do 390?
And then 430.
You just
And
picked.
it's a linear equation. It doesn't have to, yeah.
It doesn't have to be perfect. I'm not going to take my ruler out and check it.
Wow. Nice.
Okay.
Any questions?
Questions?
Good?
Yes.
All right. Let's go ahead and do our last example, but make sure you go back and do number 9 and 10.
Okay.
All right. Example 6. All right. So we have 2 graphs here. They're asking you for a real-life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? All right, look at A. Would you call that a discrete domain or a continuous domain?
Discrete.
Continuous.
All right, we have differing opinions.
Oh, I'll do discrete.
Nico, why is it discrete?
Because the plot isn't on halves.
Because you can't do half. It's very specifically whole numbers.
Yes, ma'am.
So it's just points on a graph. B would be what?
It would be
Continuous, because it includes everything in between the whole numbers.
See, that's what I was saying.
You did a great job.
Wait, do we have to put this in our
No.
Oh,
I just want you to verbally talk to me. So for A, what's a real life situation where as I started at 6 and as one thing happened, I lose one thing? Yes. Yeah, money. Money's a great one. Money could also possibly go on continuous, but we'll still work with whole dollars here. So as I spend $1 on candy, if I buy a piece of candy, well, but that would be an increasing line because as I spend $1, no, because this could be your money. So this is money and this is candy. I spend $1, I got a piece of candy. I spend another $1, I got a piece of candy.
Yeah.
So you just have to tell me something that works. Oh, look, they did money. They're buying 6 coins at an auction. All right, so what's a continuous example? So again, we start at 6 and it goes down. So what are we doing here?
Everything in between 6. So like what if you have like a 6?
6 pumpkin pies.
6-inch Subway.
A 6-inch Subway. I like that. So,
I need 1 inch, so you have 5 inches.
and then, so what's gaining here?
What's gaining?
Yeah, because you're losing the Subway sandwich as you eat it.
You're gaining fullness.
Yeah.
What's something you could measure?
You're getting fatter?
Let's go with calories.
I'm getting fat.
So, I hope 1 6-inch Subway is not going to make you fatter, measurably fatter.
Nice.
You're gaining calories, so we'll just say this is 10, 20, 30, 40, 50, 60. So as I eat some of my Subway sandwich, I'm gaining calories. Let's see what they chose. 6 ounces of gold dust, because dust can be split into.
I like the.
Your Subway sandwich was epic. I'm sorry, that was excellent. All right, good job, guys. All right, so you have 4 problems left to do, and then you're done for today.